Now we want to take a look at some of the factors affecting SN2 reactions. And first thing we'll zero in on is the substrate. And if you recall, I said when you think SN2, I want you to think backside attack. And so the structure of the substrate is going to matter here. When this nucleophile comes in to do backside attack here, he's got to squeeze in between these three groups labeled R1, R2, and R3. So, and if they are as small as they could possibly be, if they're all three hydrogens, that would be a methyl halide. So then that nucleophile is going to have no problem getting to the backside, and the reaction goes very quickly. But as you start substituting these three possible groups with carbon chains instead of hydrogens, the reaction gets slower and slower and slower. And by the time you reach a tertiary halide, so you'll find out that the SN2 reaction is completely hindered. So backside attack is completely blocked and the reaction does not happen. So tertiary halides do not do SN2 reactions. So methyl halides are the fastest, then primary, then secondary are kind of slow, but they'll still happen. Tertiaries don't happen at all. So that's our first factor affecting an SN2 reaction. Let's take a look at another substrate steric effect here. So of secondary importance involving the substrate is not only looking at the carbon with the leaving group, and in that case that's that carbon, and that carbon. The X represents here a halide. So we might also call that the alpha carbon, it turns out, for an alkyl halide. So, but you also want to focus in on this beta carbon here, any adjacent carbons to the alpha carbon. So, and the more substituted they are, it turns out that's also going to block the backside attack as well. Not quite to a significant degree, but it also is going to play a role here. So if we look at this beta carbon, this one over here on the far left is a secondary carbon. So this one right here is a tertiary carbon. And on the far right, this is a quaternary carbon. And so every single alpha carbon, on the other hand, was a primary carbon. And so these would all be labeled primary halides. You might think, oh, there's no difference in reactivity, but there is. So if they're all equal at the alpha carbon, look at your beta carbon. And the more substituted it is, the slower that reaction is going to go. And so with a secondary beta carbon, this reaction actually proceeds pretty quickly. With the tertiary beta carbon, it slows it down quite a bit. And with the quaternary beta carbon, this reaction is very slow and may not even happen. So again, you want to focus on that alpha carbon first, but if you've got all equivalent alpha carbons, then take a look at your beta carbon. How substituted that is can also slow down your backside attack. The next factor we want to look at are nucleophile effects. And if you recall an SN2 reaction, the nucleophile and the substrate both show up as reactants in that step, and then they therefore both show up in the rate law. So here we'd have rate equals K times both the nucleophile and the substrate. So, but the key here is on the nucleophile, and so since that nucleophile does show up in the rate law, it is involved in the slow step. It turns out for an SN2 reaction, that nucleophile has to be strong. So, and there's some rules for kind of memorizing who the strong nucleophiles are and figuring it out and stuff like that. And the first one you should realize is that when you have a negative charge, you are a stronger nucleophile than if you don't have a negative charge, all other things being equal. So in this case, like you might compare water to hydroxide, and while hydroxide makes our list here, water does not having a negative charge. So they're exactly analogous, but hydroxide's a strong nucleophile, water ends up being a weak nucleophile. So if you look at our list here of strong nucleophiles, most of them have a negative charge, but not all. So we see here sulfur, nitrogen, and phosphorus, even without a negative charge, are still fairly strong nucleophiles. Now, if they had negative charges, they'd be even stronger, but even without the negative charge, again, sulfur, and there's another sulfur there, sulfur, nitrogen, and phosphorus can still be strong nucleophiles, but just about anybody else, they've got to have a negative charge to be a strong nucleophile. So now I want to talk about some trends when it comes to nucleophile strength, but it's a little bit tricky here because it depends on what kind of solvent you have. Do you have an aprotic solvent or do you have a protic solvent? So first of all, the difference between those, protic solvents are capable of hydrogen bonding, so whereas aprotic solvents are not. So a protic solvent is going to either have an OH or an NH, and much more commonly an OH for organic chemistry, whereas an aprotic is not going to have an OH or NH bond anywhere in its structure. And so it turns out protic solvents solvate ions very well, like when you dissolve salt in water or something like that. And I've got that kind of diagrammed off to the right here. So we see all these lovely ion dipole interactions between the hydrogens of the water molecules and say an iodide ion as compared to a fluoride ion, so on and so forth. So it turns out because of these ion dipole interactions, that actually makes the nucleophiles more stable and therefore less reactive. So it turns out that all nucleophiles are weaker when the solvent is protic due to these ion dipole interactions. So however, the ion dipole interactions are strongest for the smaller ions to a significant degree. And so it turns out, well, something big like iodide might be a little bit weaker in a solvent that is protic as compared to aprotic. A small ion like fluoride is a lot weaker in a solvent that is protic as compared to aprotic. And so much so that the trend here is going to change. So if you look here, the trend here on the horizontal is the same in both cases. So nucleophiles get stronger regardless of solvent when they get less electronegative. So a less electronegative atom with a negative charge, let's say, stabilizes that negative charge less and is more reactive. So, but the vertical trend is going to change here. And so in aprotic solvents, that trend is exactly the same trend we see in basicity. So the smaller base is the stronger base, and we see here the same thing. The stronger nucleophile is the smaller nucleophile is the stronger one when the solvent's aprotic. But in protic solvents, it's the small nucleophiles that get stabilized the most, whereas the large ones only get stabilized a little, and so that vertical trend actually reverses. And so when the solvent's protic, it's actually your large nucleophiles are better. We often talk about the word polarizable, and the larger ions are more polarizable. They have squishier electron clouds, is how I like to phrase it, which allows them to do backside attack better and stuff like that. But big key here, though, is that your nucleophile strength trend, the vertical part of it, changes depending on the solvent. So the next thing we want to look at are some solvent effects here. And again, we've got two big classes of solvents, so those that are protic and those that are aprotic. So it turns out for an SN2 reaction and for an SN1 reaction a little bit, you're always going to need a solvent that is polar. The question is it going to be polar aprotic or polar protic? So we'll find out that for an SN2 reaction here, it is almost always better to have a polar aprotic solvent, one that is not capable of hydrogen bonding. And here I've listed the several most common polar aprotic solvents here: acetone, dimethyl sulfoxide, acetyl-nitrile, dimethylformamide, diethyl ether, tetrahydrofuran, and hexamethyl phosphoramide. So none of these structures has either an OH or an NH bond. They're all polar, but aprotic. They're great solvents for SN2 reactions, or at least most SN2 reactions. You'll find out then in any kind of undergraduate treatment of substitution reactions, we are going to oversimplify some things somewhere, and this is one of those places. So if you recall in the last slide, or a couple slides ago, most of the strong nucleophiles have a negative charge, but not all of them. So the trend I'm going to talk to you about here, with these polar aprotic solvents being best for SN2 reactions, technically is only true when the nucleophile is negatively charged. If you have a neutral nucleophile, it actually is the opposite. So, but again, I'm oversimplifying some things here. So we're going to say that a polar aprotic solvent is best for SN2 reactions in general. There are some exceptions. I'm going to ignore those entirely. So in this case, for SN2, we definitely want to use one of these polar aprotic solvents. So if you recall that your small nucleophiles are the strongest when the solvent is aprotic, but are the weakest when the solvent is protic. So it turns out, again, when the solvent is protic, your big nucleophiles are a little bit weaker, whereas your small ones are a lot weaker. Well, it turns out for these period 2 nucleophiles here, carbon, nitrogen, oxygen, fluorine, the solvent has to be aprotic. Now for all your bigger ones, all the bigger nucleophiles, they're faster if you use an aprotic solvent, but they actually work just fine when the solvent's protic. Like sulfur in particular. Sulfur is a very outstanding nucleophile, and if we use a solvent that's aprotic, it'll react fastest, but even if we use a solvent that's protic, sulfur has no problem doing SN2. Carbon, nitrogen, oxygen, fluorine, on the other hand, the solvent has to be aprotic. So just want to get that out there. So big thing here is that when you see a polar aprotic solvent, you should kind of associate that with SN2, but it's not a guarantee. If your solvent's polar protic, as we'll see, that doesn't mean you're not doing SN2. It might, but it might not. Some of the reactions work just fine for big nucleophiles in SN2 reactions with polar protic solvents. So now we want to take a look at some leaving group effects. And first thing you should know is that what makes a good leaving group is that it's a very weak base. And typically the weaker the base, the better the leaving group. So if your leaving group after it leaves is a weak base, that's the hallmark. I need something that's going to be stable and a weak base after it leaves. So if something's a strong base and not stable after it leaves, that's a bad leaving group. So in this case, the three we've already covered are the halides here. And the bigger they are, the better. So it turns out HI is a stronger acid than either HB or HCl, and that makes I- a weaker base and therefore better leaving group than either bromine or chlorine. So here we've got a size trend for leaving group ability. Iodine, the biggest, is the best. Chloride is the least desirable of the three, and fluoride typically doesn't even make our list of good leaving groups. It can act as kind of a weak or poor leaving group, but it's not a great leaving group. So, and then finally, I've got this other one here, which we abbreviate OTS. So an OTS is a big, ginormous structure. It looks something like this here. So it's much easier to abbreviate this thing, but this is it here. It's what we call a sulfonate ester. So you might see it in this chapter, and if you don't, you're definitely going to see it in the alcohol chapter later. So some classes will cover this, some won't. But the thing is, if this guy happens to leave, you're going to have a very weak base because the negative charge on this oxygen here is going to be resonance stabilized with the other two oxygens as well. So in this case, this OTS is a fantastic leaving group, even better than all the halides. So, but again, you may or may not see this in this chapter, but you'll definitely see it in the alcohol chapter either way. I want to touch on one last little example of a special case of an SN2 reaction, and that involves potassium fluoride here. And so it turns out potassium fluoride is not very soluble in a lot of organic solvents, but we can make it more soluble with something called 18 crown 6. And 18 crown 6 is an example of what we call a crown ether. You can kind of see they call it a crown ether because it kind of resembles the shape or structure of a crown here. But all these oxygens, so with their lone pairs, will solvate metal ions, and depending on the size of the crown ether, it might solvate a little bit different metal ion. Well, potassium's of just the perfect size to fit in the cavity here of 18 crown 6. And so as a result, so potassium fluoride, when we mix it with 18 crown 6, the potassium ions get solvated, leaving the fluoride ions to be what we call like a naked ion and allowing it to be soluble in different organic solvents. And so oftentimes if I want to do SN2 with a fluoride ion, here I'll use potassium fluoride with 18 crown 6, and here I can do backside attacks and replace that bromine with the fluorine. And again, we still see that inversion of configuration and stuff like that. So if you see KF and 18 crown 6, you know what it's for. So specifically, we'll use, again, 18 crown 6 with specifically KF. It's not the only case, but probably the only one you're likely to see.